Okay, so today's notes are on geometric series. It's chapter 9, section 5, and our content objective is to define geometric series and find their sums, and our language objective is to use the correct terminology to describe geometric series. So just as a quick recap, a series is the sum of a sequence. Since we're talking about geometric series, it will be the sum of a geometric sequence. So similar last time was arithmetic series, the sum of arithmetic sequences. Geometric series are the sum of geometric sequences. So we're going to jump right into the formula to find the sum of a finite geometric series. And we have Sn is equal to a1 times parentheses 1 minus r to the power of n all over 1 minus r. I'm going to define these variables for us again, even though you probably recognize them all at this point. Sn is the sum to the nth term. N is the term number or placement. In this context, just like in the arithmetic series, it's going to be the last term number. Then we have A1 is still our first term value. And R is still our common ratio. So all these variables you've seen before, they still mean the same thing, just now they're in a new order for our finite geometric series. So let's do an example. I want to determine what is the sum of the finite geometric series 3 plus 6 plus 12 plus 24 plus ... plus 3072. So we have a geometric series. I'm going to focus this real quick. We have a geometric series here, and we're going to find the sum by starting, or we're going to first start by defining our known variables. So again, just to rewrite the formula so you can look at it as we do this problem. I know right away my A1 value is going to be 3 because that's my first term value. My R value I can get by dividing the term by the previous term. So since it's geometric, I do 6 divided by 3 is 2. If I want to double check it, 12 divided by 6 is still 2. 24 divided by 12 is still 2. So my R value I can confidently say is 2. In this problem, I don't know my n value because I don't know n because I know the last term value but not the term placement. So I don't know where in the list 3072 falls, but I know it's the value of my last term. So I'm going to say I know an is equal to 3072. Problem is I don't need an, I need n. So what I'm going to have to do in this case is solve for n using my sequence formula. So solve for n using your geometric sequence formula. So because I don't know n, and that's what I need for my series formula, I'm going to use my sequence formula, which if you've forgotten is an equals a1 times r to the power of n minus 1 to solve out for n. So I'm going to plug in my value of my nth term, my a1 value, my r value, and n, and then I'm going to solve out for n. So I'm going to start by dividing by 3. And I get 1024 is equal to 2 to the power of n minus 1. If you've noticed at this step, we have a variable in our exponent. So our variables in our exponent, we can either rewrite both sides so they have the same base and set their exponents equal, or use logs. So again, the stuff from last unit is going to come up again because we're going to either solve with logs or rewrite both sides with the same base. Since this problem I can rewrite the left side to have the same base as the right, I'm going to do that. So I'm going to rewrite 1024 as 2 to the 10th and say that's equal to 2 to the n minus 1. So then 10 equals n minus 1, 11 is equal to n. So now I know my n value. I know I'm finding the sum to the 11th term in this sequence. So I'm going to use that to plug into my formula, my series formula, and solve out. So step 3, I'm going to substitute into the finite geometric series formula. And then evaluate. So I say S11 is equal to 3 times 1 minus 2 to the 11 over 1 minus 2. When I plug that into my calculator and evaluate it out, I get S11 is equal to 6,141. So that would be my sum of the first 11 terms of this series. So my last step that I did was evaluate or calculate out. All right, make sure you write down any questions on that example. I'm going to flip the page and do an example with our sigma notation. So make sure you write down questions on this. I'm going to flip the page. We're going to do our second example very quickly. It's just using our sigma notation, the same thing as yesterday. So I have this formula. This is asking me to find the sum from the first term to the 20th term. So I'm given this sequence formula. So I'm going to have my steps will be very similar to the last problem. I just have different known and unknown values in this case. So first step, I'm going to define my known variables. And in case you want the formula in front of you, here it is. I know that n in this problem is going to be 20 because I'm finding the sum to the 20th term. And then I know my r value is 1/2. And I know my a1 value is 4 because this matches up to my geometric series formula. So a1 times r to the power of n minus 1. If you weren't sure for a1, you could also solve for a1 by plugging that value in. So you have 4 times 1/2, the 1 minus 1. 1 minus 1 is 0. 1/2 to the 0 is 1. 4 times 1 is 4. So you either can recognize it there, or if it's not written in this form for some reason, or if you're not quite sure what I did, plug in 1 for n, solve it out, and you know your first term value is 1. So then all I have to do is substitute into the formula. Sorry, I forgot the word finite. It's important because we're going to learn about infinite in just a second. So I'm plugging into the finite geometric series formula. So I have S20 equals 4 times 1 minus 1/2 to the 20 all over 1 minus 1/2. So notice I also put the 1/2 in parentheses for my r because I'm raising the whole r to the power of 20. So if you have a fraction for your r value, it needs to be in parentheses when you raise it to the power. It does make a difference when you plug it into a calculator. And then my last step is to evaluate that. And again, you can use a calculator. Make sure you plug it in pieces and are careful as you plug it in, but you should get S20 equals approximately 8. The sum to the 20th term is approximately 8. It's actually 7.99999 something, but if we round to 2 decimal places, it will be 8. All right, so that's it for finite geometric series for now, but now I want to talk about infinite geometric series. And these are fun. They tie into the asymptote stuff we talked about previously. But infinite geometric series, before I go, I want to do kind of a visual example, and I'll draw this out for you in a second, but it's easier to do with pieces of paper first. So if I had a geometric series and I started with just this one little square, or this one little rectangle here, but then I wanted to add on half of that square. So I'm going to take 1/2 of, or add 1/2 of the area each time. So if I add half of the area of that rectangle, I get that shape. And then I'm going to add half of that again. So if I keep adding half of the previous area, I'm going to get a shape that looks like this. And as I continue to do this, you might notice that my squares get small, or my rectangles get smaller and smaller. So it's decreasing in value each time. As I'm doing this, note that it never, as I do this, it will never extend beyond the edge of that square. So when you can find the sum or the area or the total of the infinite geometric series when your R value is less than 1, because it will never extend beyond a certain amount, because it will continue to get smaller and smaller and never surpass a complete area. So I'm going to draw that visual that I just cut out real quick so you can have it in your notes. But if I had a square, cut it in half, and continued to cut it in half forever, it still would never extend beyond the area of this square. So I could keep cutting it in half indefinitely. This area would never extend beyond the full area of the square. So in this example, I just took the area and multiplied by 1/2. And then the area will never be greater than the initial square, or than the square. So this is a visual example of what an infinite geometric series, and sort of shows you why it can work. So the formula is going to be first of all, you can only use this when the absolute value of R is less than 1. So you cannot find the sum of an infinite geometric series if your R value, if the absolute value of R is more than 1. So if we wanted to work with 1/2, we could find the infinite sum of that. We cannot, however, find the infinite sum if R is 2 or 3, because that would continue to increase forever rather than decrease, and that it would diverge rather than converge if we're using technical vocab. So it only works when it's converging or when your R value is less than 1. So our formula is just S, and we don't have an n value because it's to the infinite n value. So S is equal to A1 over 1 minus R. And we know S is the infinite sum. A1 is the first term value still, and R is our common ratio. So just for the sake of space, I'm going to flip the page to do our last example, but it will be pretty quick. So last example we're going to do together. I want us to determine what is the sum of 1 plus 1/2 plus 1/4, so on and so forth forever. So first thing, I always want you to check this. Determine if the absolute value of R is less than 1. So to do that, I'm going to do term divided by the previous term. So 1/2 divided by 1 is still 1/2. If you want to double check that, you'd have 1/2 divided by 1/4. That's a quick refresher, since I think some people have probably forgotten. When you divide fractions, you actually can just flip the bottom one or flip the second one and multiply straight across. So when I'm dividing 1/2 by 1/4, it's the same as multiplying 1/2 times 4 over 1. So then I end up with 4 over 2. Sorry, I wrote those backwards. It's 1/4 divided by 1/2. Sorry. My bad, everyone. But it's 1/4 divided by 1/2, term divided by the previous term. My bad. 2 over 4. Sorry about that. Sorry. Equals 1/2. Otherwise, we would not have a common ratio. So that is indeed 1/2. R is 1/2. There we go. Now all I do is define my variables. And then I'm going to substitute it. So my variables for S equals A1 over 1 minus R. A1 is equal to 1. R is equal to 1/2. If I plug that in, I get 1 over 1 minus 1/2, which is 1 over 1/2. In this problem, I substituted that value. And then I'm going to evaluate. So I have 1 divided by 1/2. That's 1 over 1 times 2 over 1, which is just 2. So my infinite sum of that sequence is going to be equal to 2. That's all for today. Make sure you write down any questions, comments, or concerns you have so we can go over them together in class.